The Geiger counter measures the intensity of high-energy radiation such as alpha, beta, gamma, and X-rays in an environment. It does this using quantum mechanics and electricity. First, a vacuum environment is needed to allow the chamber to be filled with the desired gas. One side of this environment must be made of a material that allows the radiation to pass through. In this way, radiation can enter the environment while preserving the vacuum structure. The Geiger counter's chamber is filled with gases that can be ionized by high-energy radiation such as alpha, beta, gamma, and X-rays. These gases are noble gases like helium, argon, or neon. Since high energy is required to ionize these gases, they are chosen to prevent the detector from being affected by external influences. To direct the ionized gases, negative voltage is applied to the sides of the chamber. To direct the electrons resulting from ionization, a positively charged rod is placed at the center. This voltage must be high because we want to detect every electron released through ionization. If the voltage is low, the probability of electrons recombining increases. However, the voltage should not be too high either. If it is, it may ionize the gas in the chamber by itself, resulting in faulty radiation measurements. The extra current caused by electrons being pulled by the central rod is measured with an ammeter, and the radiation intensity is determined in this way. Now that we have learned which components the Geiger counter includes and why, let's examine how it works step by step and observe whether any problems may arise. One side of the Geiger tube is covered with glass. Radiation entering from here hits the noble gases that are abundantly present inside the tube and ionizes them with its energy. The ionized noble gas is positively charged and is attracted by the negatively charged shell. The electron resulting from ionization is attracted by the positively charged rod at the center. Since this voltage is high, both the electrons and the ionized gas atoms can further ionize other noble gases and even hit the negatively charged shell and emit new electrons. The electrons and ionized gases resulting from these events undergo the same processes, potentially creating a continuous electron cycle in the tube. As a result, even in the absence of radiation, a reading may be observed on the ammeter. This is an undesirable situation and must be prevented. To solve this problem, a small amount of group 7 halogen gases is added to the environment. These gases prevent the formation of an infinite cycle in the tube by absorbing energy and inhibiting secondary ionizations, thus controlling the ionization chain. Finally, the electrons captured by the positively charged rod at the center generate a current. This resulting current is measured with an ammeter, and the radiation intensity in the environment is indirectly determined. The Geiger counter is a sensitive detector that works based on a quantum mechanics principle to detect ionizing radiation. With a well-designed gas environment, proper voltage setting, and correct use of quenching gases, the presence and intensity of radiation can be reliably measured. This system has become an indispensable tool in the fields of nuclear physics and radiation safety due to its simple structure and effective operating principle.